The nucleus, part 5. Now we're going to talk about the binding energy. In this paragraph, we're going to determine the formula that gives the binding energy of a nucleus. That is the minimum energy necessary for separating the nucleus into its nucleons. We're going to start by the mass defect of the nucleus. In this table, this is the column containing certain nuclei. Helium containing 2 protons and 4 nucleons. That is to say 2 protons and 2 neutrons. The number of neutrons is calculated by the formula n equals to A minus Z. This is Z. This is A. 4 minus 2 equals 2. The helium nucleus has 2 protons and 2 neutrons. The lead nucleus, on the other hand, contains 82 protons and 206 nucleons. That is to say, 124 neutrons. In this column, we have the mass of the nucleons of the nucleus. It is the mass of the protons, which is the number of the protons multiplied by the mass of 1 proton, plus the mass of the neutrons, which is the number of neutrons multiplied by the mass of 1 neutron. When performing the calculations, we find that the mass of the nucleons that form the helium nucleus is 4.03186 U. The mass of the helium nucleus equals to ZMP plus NMN. Z for helium is 2 and N is 2. The mass of a neutron and that of a proton are given here, so we can find that the mass of the nucleons that form the nucleus is 4.03186 U. Similarly, we can calculate the mass of the nucleons that form the lead nucleus. Here we have the mass of the nucleus. There is a difference between the mass of the nucleus and the mass of the nucleons that form the nucleus. The mass of the nucleus is the mass of its nucleus as a whole, as one entity. By using a spectrometer, we can measure the mass of the nucleus as one entity. It is 4.0026 U. Here it is 205.94745 U. When comparing the two values, what do we notice? We notice that the mass of the nucleons that form the nucleus is greater than the mass of the same nucleus as one entity. That is to say, after the formation of the nucleus, there is a loss in the mass. Look here. Here we have 4 nucleons, 2 protons and 2 neutrons. When united, will form the helium nucleus. When combining the nucleons to form the helium nucleus, the mass decreases from 4.03186 U to 4.0026 U. The mass decreases. There is a loss in mass. This loss in mass is called the mass defect. The mass defect of a nucleus is equal to the loss in mass. The mass defect of a nucleus is equal to the loss in mass. Its symbol is delta M. It equals to the mass of the nucleons in the free state when they are not bound together. It is the mass of the nucleons in their free state minus the mass of the nucleus as one entity after the binding of the nucleons. This equals to ZMP plus NMN minus MX. This is the mass defect, which is to be memorized. The mass defect is the difference between two masses, the mass of the nucleons before they form the nucleus minus the mass of the nucleus after its formation as one entity, as a whole. When passing from the free unbound state to the nucleus state, there is a mass defect or a loss in the mass. The formula that gives the mass defect is given here. ZMP plus NMN, which is the mass of the nucleons before the formation of the nucleus, minus the mass of the nucleus. Now let's talk about the binding energy. These are the nucleons of a nucleus in the free state. The nucleus is XAZ. The mass is ZMP minus NMN. These nucleons form the nucleus XAZ when joined together. We obtain a nucleus of mass that is less than the mass of its nucleons in its free state. We say that there is a mass defect. It equals to ZMP plus NMN minus MX, which is the mass of the nucleus. When the nucleus is formed, a certain amount of mass is lost. When going back to Einstein's formula, each body of mass m possesses an energy called the energy of the mass, which is equal to mc squared. The mass is a form of energy. The mass can transform into energy. This is what Einstein said. Here we have a lost mass. This lost mass will transform into energy. That is to say, during the formation of the nucleus, there is a release in energy. Release in energy. This energy is equal to the lost mass. So the lost mass will transform into energy. The energy liberated during the formation of a nucleus is equivalent to the energy of the lost mass. That is to say, the lost mass multiplied by c squared. The energy of the mass is m times c squared. Hence, the energy of the lost mass equals to the lost mass multiplied by c squared. The lost mass is delta m. This is the energy liberated during the formation of the nucleus. Delta mc squared. This is also called the binding energy of the nucleus. If we want to separate the nucleus into its nucleons in a reversible manner, for example, during the formation of the nucleus there is a release in energy equals to delta mc squared. So if we want to separate the nucleus into its constituent nucleons, we need to supply an energy also equal to delta mc squared. Hence, the binding energy equals to delta mc squared. That is to say, it is the minimum energy required to separate entirely the nucleus into its nucleons. Thus, the binding energy is the minimum energy required to separate the nucleus into its nucleons, or it is the energy released during the formation of the nucleus. This is the expression of the binding energy of a nucleus. Binding energy of a nucleus. By definition, it is the minimum energy that is necessary for entirely separating the nucleus into its constituent nucleons. This is the minimum energy necessary for separating the nucleus into its nucleons. Now let's solve an application. This is the mass of the nucleons that form the lead nucleus. And this is the mass of the lead nucleus itself. We have to find the binding energy of the lead nucleus. So what do? We use the formula, the binding energy equals to delta m c squared. Delta m is the mass defect of the nucleus. What is the mass defect? It is equal to the mass of the nucleons that constitute the lead nucleus minus the mass of the lead nucleus itself. 207.67 minus 205.9545. The answer is 1.6955 U. This is the mass defect. Note that when calculating delta mc squared, it is easier to convert from U into mega electron volts per c squared. So what do we obtain? 1.6955 multiplied by 931.5 mega electron volts per c squared. This is approximately 1580 mega electron volts per c squared. When substituting here, we obtain the binding energy as 1580 mega electron volts per c squared multiplied by c squared. So we obtain 1580 mega electron volts by simplifying by c squared. This is the binding energy of the lead-206 nucleus. So for completely separating the lead nucleus into its nucleons, we need to supply to the nucleus an energy equal to 1580 mega electron volts. In this case, lead is Pb2O682. If we want to calculate the binding energy per nucleon, or the average energy necessary for separating one nucleon from the nucleus. To separate all the nucleons, which are 206 in this case, we need to supply an energy of 1580 mega electron volts. So how much energy is required to separate one nucleon from this nucleus? We need 1580 mega electron volts divided by 206. 1580 are distributed over all the nucleons. Each nucleon needs this energy. This is called the binding energy per nucleon. In this case, it's equal to 7.67 mega electron volt per nucleon. This is the binding energy per nucleon. binding energy per nucleon. Hence, for separating each nucleon from the nucleus, we need to supply an energy of 7.67 mega electron volts. This is a very important indicator for comparing the stability between different nuclei. This is an extremely important indicator for comparing the stability between different nuclei. Let's take another example. Consider the iodine 139 nucleus. The masses of the protons and neutrons are given in the free state. The mass of iodine nucleus is 138.897 U. We need to calculate the binding energy and the binding energy per nucleon of this nucleus. We need to calculate the binding energy and the binding energy per nucleon of this nucleus. The binding energy is equal to delta m c squared. Delta m is the mass defect. The mass defect is equal to the mass of the nucleons that form the nucleus minus the mass of the nucleus. The protons and neutrons form the nucleons, so ZMP plus NMN minus the mass of the iodine nucleus. Z equals to 53. This is Z. And this is A, 139. Z equals to 53. The mass of a proton is given here. N is the mass of a neutron. 139 minus 53. The mass of the neutron is 1.008665 minus the mass of the iodine nucleus, the mass defect in this case is equal to 1.262915 U. Convert this value into mega electron volts per c squared. 1 U equals to 931.5 mega electron volts per c squared. So we multiply by 931.5. So we get 1176.4 mega electron volts per c squared. This is the mass defect of the iodine nucleus. Returning back to the formula of the binding energy, delta mc squared. Delta m is 1176.4 mega electron volts per c squared multiplied by c squared. Simplify by c squared. The binding energy becomes equal to 1176.4 mega electron volts. This is the binding energy for the iodine nucleus. We still need to calculate the binding energy per nucleon. The binding energy per nucleon is equal to the binding energy divided by A. 1176.4 divided by A, which is 139. So we obtain 8.4 mega electron volt per nucleon. So to each nucleon corresponds 8.4 mega electron volts per nucleon. So to separate a nucleon from the nucleus, we need to supply an energy of 8.4 mega electron volts. In part B, the binding energy per nucleon of the lead 206 nucleus is 7.67 mega electron volts per c squared. Which of the nuclei, iodine or lead, is the more stable one? When comparing the binding energy per nucleon for the iodine and the lead nuclei, this is 7.67 mega electron volts, and this is 8.4 mega electron volts. This is greater than this. Hence, we need more energy to separate a nucleon from iodine. Therefore, iodine is more stable than lead. Always, the more stable nucleus has a greater binding energy per nucleon. When comparing the stability of nuclei, we compare their binding energy per nucleon. The one that has a larger binding energy per nucleon is the more stable nucleus.